All right, so 11 o'clock, time to get started. Today we're going to talk about normal stress that's caused by bending a beam. If we apply a moment and bend something, it causes a normal stress, and that's our goal today, is to come up with this formula that we can use to calculate that normal stress that's due to bending. But before we get into that, I'll just mention I sent out an email to this effect yesterday afternoon, sometime late yesterday afternoon, saying that I did finish grading the test and the grades were posted in the grade book in Canvas, as well as the solution is posted in Canvas. So if you didn't get that email, just wanted to pass that information along. Just FYI, if you're curious, the average on the test is actually a little bit higher than the first one. 78.4 was the average, which that's pretty good. That's about where the average should be. Some did better than they did the first test. Some did worse than they did the first test. Some did about the same, but that's what the average came out to be. And nobody made 100. If you're curious, 98 was the high score this time. Uh, there it goes. So anyway, that's just information purposes. Um, Again, if you got questions, concerning your test, then let me know. We'll try to clear up anything. But as I said a minute ago, today we're going to focus on deriving this formula for, again, a lot of times referred to as bending stress, but the normal stress due to bending. And I've said before, I try not to, spend too much time deriving stuff in theory and spend the majority of the time, working problems. But there are a few things that I think are important enough that you need to see where it comes from. And this formula we're going to derive today is one of those. It's one of the most probably important and most used formulas that somebody in the real world doing stress analysis on beams is going to use this a lot. And you really need to see where this formula comes from. That we didn't just pull this thing out of the air. So uh, what we're looking at is a beam, some length L, and the x-axis, the x direction is the longitudinal axis, and if we apply a moment to bend this beam, we talked about yesterday when it causes this thing to deform. Part of the beam is going to be in tension, part of it's going to be in compression. And the formula we're going to come up with today will tell us what the magnitude of that tensile and compressive stress is. One thing I may have mentioned yesterday, but if I didn't, I want to make sure everybody's with me here. We're assuming that we have no axial loads applied. So the axial force P is going to be 0. We're just bending this. When we started out analyzing normal stress in axially loaded members, remember, we were just applying axial loads, no bending. Well, we're doing the opposite now. We're just bending, no axial loads. Now, when we get to chapter 8, we're going to combine the two. But we're not there yet, but it's coming. We're going to get there eventually. All right, so that's the assumption we're going under, that we're just bending this thing. And so if I can attempt to draw this deformed beam, let's see, do my best. I'm sure this will not come out too pretty, but I'll do what I can. Not too bad. We'll go with that. For me, that's pretty good. All right. So one thing I did mention yesterday, toward the end of class, was that there's going to be one surface right down the middle of this thing that's not going to deform as far as change in length. So if this beam has some initial length L, this would still have length L. This is what we call the neutral surface. So I'm just abbreviating neutral surface in S. So that surface down the length of the beam doesn't deform. In this case, if we're bending it this way, and it deforms like this, the top is getting shorter. In fact, anywhere above that neutral surface is getting compressed and will be shorter. Anywhere below that neutral surface is getting stretched. It's in tension, and it's going to get longer. Right? So we're going to define this distance from the center of curvature out to that neutral surface. We're going to call that distance rho, and that would be what we call the radius of curvature. That's what rho is. It's a radius. It goes from the center of curvature to that neutral surface. Now, I can tell you, the approach we're going to take is how we're going to eventually get our formula for stress. So, Nathaniel, you can't hear me? Let's see. Dominic replied that he can hear me. Okay, Nathaniel fixed it. Good to go. All right. All right. So as I was saying, just kind of big picture, you want to kind of keep in mind the approach we're taking and how we're going to get this formula for stress is we're first going to see if we can determine what strain is. And if you remember, it's all my days run together now, but somewhere back in the early material, we talked about Hooke's law, which is the relationship between stress and strain. So what we're going to do is we're going to see if we can derive a formula for strain, and then we can use Hooke's law to get stress. Anyway, so that's kind of keep in mind how we're going to get there. So what I want to do is look at some arbitrary surface. So let's just say, let's consider maybe we'll call it length AB. Well, we'll just pick two arbitrary points, AB here. At some arbitrary, I'm going to abbreviate, arbitrary distance y from the neutral surface. So we're gonna come up here some arbitrary distance y. Right, remember our coordinate system. If we look at the cross section, we said x was the longitudinal, y was the vertical, z was the horizontal. So y here would be the vertical direction. So we're going to look at this surface, draw this line, and we'll call this length AB. So we're just going some arbitrary distance away from that neutral surface, and we're going to look at that length and see if we can determine what's the change in length. What's the difference between this length and the original length, undeformed length of our neutral surface. Well, if this is some distance y away from the neutral surface, then this distance, this radius, would be whatever rho is minus that distance y. That would be the radius from the center to that surface. Well, all we're going to do is use what we know, about arc length. S is equal to r theta. So this length, undeformed length of the neutral surface, the radius is rho, and theta would be that angle. We also know, right, the length of AB would be that radius times that angle. So it would be rho minus y times theta. All right, so pretty straightforward at this point. That would be the length of those two surfaces with respect to the radius and that angle. Now, if you remember normal strain, and remember, I'll come down here below. I have a little more room. Notation-wise, we use epsilon. So this is my attempt at the Greek letter epsilon. So we want to know what is the normal strain, the strain in the longitudinal or the axial direction, which is the x direction. Right? It's just changing length over length. Right? That was how we define strain. So we would take the length of AB minus the undeformed length, divide by the undeformed length. Well, if we substitute in what we know, this is rho minus y times theta. L is rho times theta. And in the denominator, again, we have rho theta. And then we do a little simplifying. Now, if you multiply this theta out, right, you're going to get a rho times theta, and we have a minus rho times theta. So they essentially cancel out. In the numerator, all you're going to have left is minus y times theta. In the denominator, rho times theta. And the thetas cancel out. And so what we've got then is our normal strain for that surface AB is just minus y over rho. And again, this distance y is some distance, and it's measured from that neutral surface. And positive up. Just remind you our orientation of our coordinate system. Positive y is defined to be up. And notice that this will give us a result that corresponds to what we did previously, right? This will tell us if we apply this moment and bend it this way, if we go above the neutral surface, y will be positive. Well, if you plug a positive y in here, you get a negative strain. That's indicating compression. It's getting shorter. If you came down here some distance y, right below, y would be negative. You put in a negative y times that negative, and you would get a positive value, positive strain, indicating tension and stretching. So our sign convention we're using will still means positive is going to correspond to tension, negative is going to correspond to compression. Same as before. Right. All right, so questions at this point, how we got this formula for the strain. Right. As I said a few minutes ago, how we're going to get to stress is we're going to apply Hooke's law. Remember, Hooke's law says normal stress is equal to E times normal strain. E here being our modulus of elasticity, that's the material property. Now, one thing to remember, though, this is true only if you're in that elastic or linear region. Again, elastic here, if you're looking at the stress strain diagram, the linear part, this is where stress is not, we'll use proportional limit. as I've said a few times already, you're going to find a lot of our formulas we use in stress analysis are based on Hooke's law, which do have some limitations in that it's only valid for stresses less than that proportional limit. But as I've said before, in the real world, that's where your stresses will be. Right? We're not going to intentionally have a structure that's being permanently deformed. So we're going to design the structure so that the stresses are less than that proportional limit, and Hooke's law does apply. So all we're going to do is take what we just got for strain, plug in here for strain, and we get stress is equal to minus E times Y over rho. Now, it would be nice if we were done, but we're not quite done yet, because we want something, we want to do better than this formula. But we do have a formula now for stress. But I'll go ahead and tell you what we would like to do is get rid of that rho, because we would rather have a formula for stress that was in terms of the moment that's applied as opposed to the radius of curvature. And that's where we're going to continue this in just a second. But even at this point, there's some useful observations to be gained. One thing is, note that our normal stress sigma is a linear function with respect to y. I think I drew a picture of what the normal stress distribution looks like yesterday, and I told you we would see how we knew it's linear today. Well, we know now that this is going to be linear. If you look at this stress distribution, if we bend it this way, our neutral surface, up here is going to be compression. It's going to be pushing in on that surface. Down here below, it would be in tension. It's going to be pulling on that surface. It's linear, right? Y is the distance you get away from that neutral surface. So the further you get away from the neutral surface, the larger the stress. Right? So that's how we know our maximum is going to occur at the top and bottom surfaces. So one's going to be your maximum tension. My picture is not off the page there. All right, so one's going to be the maximum. This would be the maximum compression. This would be the maximum tensile stress. But they're going to occur here on that top and bottom surface. And stress is going to be zero at the neutral surface. Sigma 0 here. Right, so this verifies and confirms what I mentioned yesterday. All right, so before we continue our journey here and try to get rid of this rho, questions at this point? How we got to this formula for stress. All right, speak up if you need a second or two more to copy anything down before I go to next page. Move the page up. When you say up, you're talking this way, Dominic, or the other way? Other way. Is that better? Okay. Are we good now? Anybody need another minute or a few seconds, or we're good? All right, so we're going to a clean sheet now. So really, we need two things. Now, I mentioned one, we want to get rid of that row, and we'd like to have the moment in there instead. But there is one other thing that we also need, and I'll write this. We need to find or determine or whatever you want to say. Actually, two things. First, we need to find the location of the neutral axis. Now, remember, the neutral axis is the axis on the cross section that corresponds with the neutral surface. If I draw a picture again here. Yeah, I better not go 3D. No. So if we're looking at the beam, right, this was our neutral surface. Right, but if we're actually looking at the cross section, where the x-axis is coming straight out of the paper toward us, the z-axis is what we call the neutral axis. Right? It's going to correspond to here. Z would be coming straight out at us. So when you're looking at the cross-sectional surface area, that's what we refer to as the neutral axis. Because if you remember, that formula was based on y, which y being the distance away from that neutral axis. Well, we got to know where the neutral axis is located. Otherwise, we don't know what y is. So that's one thing we need to find or determine. The second one is what I had mentioned before. We want to know what's the relationship between rho and m. All right, so those are the two things that still need to be determined. Is one, come on, let's focus for me. There we go. Where that neutral axis is located, and what's the relationship between rho and m? We would like to replace that radius of curvature with our applied bending moment instead. All right, so let me we'll draw another picture. Let's see, we'll do my best here. We'll try to draw this in 3D so we can see. So what we're looking at is a big cross section of a beam. And I've said this a few times, but I'll repeat it. The fact that what I'm drawing is rectangular is just an arbitrary choice because it's easy to draw. What the cross section looks like doesn't change anything here. So let's see if I can draw straight lines. We've got our x-axis, again, running longitudinally. Y is the vertical, and our z-axis, again, which is our neutral axis, is the horizontal direction. Now, what we're going to do is I'm going to break this up into infinitely many little pieces, little bitty rectangular areas, little differential area I'll call dA. Now that little differential area is going to be some distance y away from the neutral axis. Now, let's go back and use one of the first formulas we came up with. Right? We defined normal stress as being P over A, where P was the normal force. Right? It was the force perpendicular normal to the surface divided by the cross-sectional area. Well, one thing we didn't really talk about or discuss then was that if the normal stress is P over A, you can actually get the force, right, by taking the stress and multiplying times the area that stress acts
For
over.
telemarketing purposes, to be placed on our do not call list.
I'm sorry? All right. But we can get the force by taking the stress and multiplying times the area that it acts over. Well, if we look at this little differential area, there's going to be some differential force. We'll call it dP. That would be the force that's acting on that little differential area. Well, we can use the same idea here then and say that that little differential force dP must be equal to the normal stress times that area that it acts over. That would be the force acting on that little differential area dA. If we want to get the total force, total force P that's acting on that cross-sectional area, we just integrate. Right? We just add up all those little differential forces dP, add all those up, and that would be the total force P that's acting on that surface area. Well, we know from just a minute ago that the stress was minus EY over rho. I'm just substituting what we got a second ago in there for the stress. Well, E and rho are constant, so we can factor those out. I'll factor out the negative sign as well. So what we have is minus E over rho times this integral dA. But remember one of the first big assumptions we made at the beginning before we started this was that we're assuming no axial loads. So again, if our axial force P is 0, then this integral's got to be 0. Because remember, E is not 0. Unless if you have material there, you have a modulus of elasticity. That's the only other way it could be 0. Either E is 0 or that integral is 0. Well, E is not 0, so the integral must be 0. Now, you may or may not recognize that integral, but I will remind you, you saw this integral in statics when you talked about sinusoids. Right? When you probably first started covering centroids in statics, you probably did it for areas where you had to integrate. And then I suspect you did it for areas, what we call composite areas, where you did not have to integrate. But the centroid location is the integral of y. Oh, I left my y out up here. I knew something went right. I factored out the e and the y, the e in the rho, but I left my y out. You're all supposed to pay attention and catch things like that and speak up. So,
okay.
So we factored out the e and the rho, and we still had a y left. I just didn't write it down. It magically disappeared. Right? This was the formula, the integral formula, for calculating the centroid location. Well, if you notice, that numerator is the same integral we got now. So that integral, y dA, is equal to the area times y bar, which is the centroid location. Well, but I just said this integral is 0. So if this integral here is 0, then that means either a is 0 or y bar is 0. Well, if a is 0, we don't have a beam, right? We have no cross section. So the only way that's 0 is if y bar is 0. So y bar, again, is the distance to the centroid. Well, if y bar is 0, then what does that tell us? The distance from our z-axis, our neutral axis, to the centroid is 0. And this is the result we're after. The neutral axis must pass through the centroid. Of the cross-sectional area. So if we're looking at this cross-sectional area, our z-axis, our neutral axis, has to go through the centroid. And we have to know that, otherwise we can't calculate the stress because we don't know how far we are away from the neutral axis if we don't know where the neutral axis is. But now we know where the neutral axis is. It goes through the centroid. This is why you learn how to calculate centroid locations in statics. Well, one of the reasons, not the only reason, but one of the most important reasons why you learned how to locate centroids was because of this fact right here. If you don't know how to locate a centroid for an area, you can't calculate the stress. All right, so that answers our first question. Our first question was, where's that neutral axis? We now know it's at the centroid. All right? Any question about that? All right, well, now let's turn our attention then to the second question. The second thing we need to determine is see if we can get a relationship between the moment and that radius of curvature. All right, so what we're going to do now, we're going to refer you to still looking at the same picture, but now let's sum the moments about that neutral axis. So we're going to sum the moments about that z-axis, our neutral axis. And if we go with right-hand rule, if this is our z-axis, a positive moment would be in that direction. Again, I got my right hand thumb in the positive z direction. Direction my fingers curl is defined to be the positive moment. And so that's what we're gonna define a positive direction that way. So we're going to start by getting the moment caused by that differential force dP. So we'll call this the differential moment about the z-axis. Now, if positive is this direction, it's going to be negative. But we would just take that force times that perpendicular distance away from the z-axis, which is y. So it'd be minus that differential force times the distance y away from the z-axis. But I know from up here, dP, that differential force, is the stress times the differential area times y. And we're going to do the same thing we did up here. To get the total, we integrate. So to get the total moment, mc, it would be the integral over that entire area of minus, I'm going to rearrange things so I put my dA at the end. So minus y times sigma dA. making the same substitution we did up here as well. For that stress, I know is minus EY over rho, right? Substituting what we determined the stress was here. But in this case, we can still, like we did before, we can factor out the E and the rho. The negative times the negative is positive, so we can get rid of the negative signs now. It's positive. And I'm not going to leave my y's out this time. Y times y is y squared. So this is the moment about the z-axis. Now this integral you should also recognize. My pen's not right. There we go. Just like this integral up here you had seen before when you did centroid in statics. This integral you also saw in statics. You may or may not recognize it. Anybody? I'll take a pause here. Somebody recognize what that integral is? You saw it in statics.
Is it a moment of inertia?
That is correct. It is the integral for moment of inertia. This would be the moment of inertia about the z-axis. This is the moment of inertia about the z-axis. So we're just going to go ahead and replace that integral with IZ. So what we've got now, up a little bit, is we've got MZ is equal to EI over rho. So we just replace that integral with I. And understood it's IZ. Most of the times you'll see that subscript left off and it's just understood. Everybody knows where this formula, what this formula is. It's the moment of inertia about the z-axis. So if we take that and we solve for rho, I get rho is equal to EI over M. This M is our moment. All right. So that's what we were after. Now, when we take this and go back and substitute that in for rho, we will get a formula for stress that's in terms of the moment instead of the radius of curvature. But I'm going to start on the top of a new sheet before I do that. So again, if you need a second or two longer, speak up. Everybody got this? I'm assuming then. All right. So we had previously we said the stress was minus EY over rho. That was the first thing we came up with. We just came up with this one, that rho is equal to EI over M. So we're going to take that, substitute in here, and we get the stress is minus EY. If we divide by rho, we're going to multiply by the inverse, M over EI. Well, the E's cancel. And what we have then is, I'll come down here. Stress is minus My over I. That's the formula we're after. Not real complicated formula. If you want to know what the normal stress is due to bending, it's just minus M, where M is the bending moment. Y is the distance you are away from that neutral axis, which we now know goes to the centroid. And the denominator is just the moment of inertia about that neutral axis. This is one of the main reasons you learned how to calculate moments of inertia in statics. Again, not the only reason, but one of the main reasons. If you can't locate a centroid and you can't calculate a moment of inertia, you can't calculate stress. That's why those things are so important for you to learn in statics. And we'll find out here going forward, starting next week, how well you learned how to do that in statics. Because I can tell you, that's where the vast majority of mistakes get made. I see students in mechanics and materials trying to calculate bending stress. You can plug in this formula. That's not the problem. The problem is not calculating the correct location for the centroid, which means y is going to be wrong, or you can't calculate the moment of inertia, or you don't really know how to do it well enough that it takes you way too long to accomplish those two things. Those two things you should be able to do quickly and correctly, and that's locating centroids and calculating moments of inertia. All right, but let me write some of this out here just to make sure there's no confusion. M, this is the bending moment. About the z-axis, all right, which remember this is our neutral axis. Those two coincide. And remember this goes, neutral axis goes through, and squeeze this in here, right small, centroid. No, in fact, I'm going to point that out in just a minute. This formula, the sign convention is such that the negative stress is going to correspond to compression, and a positive corresponds to tension, just like we always have done. And I'll point it out, and we'll talk about that in just a second. Y here is, again, the vertical distance from the neutral axis, and positive is up. I, again, is our moment of inertia about that neutral axis. And again, it's the moment of inertia, I should add, of the entire cross-sectional area. So whatever that cross-section looks like, now here's where the cross-section matters, whether it's rectangular or circular or like an I-beam. What the cross-section looks like will have an effect on what the moment of inertia is. But it had no effect at all in us deriving this formula. But again, based on our sign convention here, notice our positive moment we defined earlier right, that's a positive moment, right? A negative moment would be one that bends it this way. So if we have a positive moment and we have a positive y, this is going to give me a negative stress, which corresponds to compression, right? Because if y is positive for a positive moment, anywhere above that neutral surface or neutral axis is in compression. So this formula, it's going to give you negative values corresponding to compression, positive values going to correspond to tension. Because if we have a positive moment and y is negative, that means we're below our neutral axis. That's in tension. But if y is negative times a negative, you get positive. So if you use the proper orientation of your coordinate system and use this as a positive moment, this is a negative moment, this formula the signs will correspond to tension and compression. Positive tension, negative compression. All right. Now, I will point out here, this is still, back when we did normal stress in axially loaded members, I emphasized, hopefully, that it was important to differentiate between tension and compression. Right? And the reason for that was buckling. If you got an axially loaded member in compression, it could fail by buckling as opposed to the material failing due to a high stress. So it's still important when we're bending to differentiate between tension and compression. Slightly different reason. Similar, it has to do with buckling, but when you bend something, it's not going to buckle like, I'm going to stick this end down here at the bottom. What we did before, you got an axially loaded member like this in compression. This is what we call buckling, right? When it would bow out like that, right? Or let's see if I can find I used my ruler the other day for bending. Now, I don't know if this will show or not, but yeah, if I push in on it, that's all I'm doing is pushing in on the ends. It bows out. Right? That's called buckling. Right? But if we bend a beam, depending upon what the beam looks like, we could have what we call local buckling. Like the whole thing doesn't buckle. You see this quite a lot if you have, for example, one of the most common shaped cross sections for beams is an I-beam. All right, well, if we bend this thing, say we bend it this way, all right, we apply some moment here. Everywhere above our neutral axis is going to be in compression. Well, that's not going to buckle like this axially loaded member. But if you have really wide, thin, we'll discuss some terminology later. These are called the flanges. So this would be the flange. What you could see is that flange will buckle. And again, it's not going to bow out like that. What you would see is basically looks like waves. What you would see is this, the flanges here on that I-beam are going to ripple. That's what we call local buckling. Now, that's not covered in this class. Some of you, only one I know for sure, I can tell you, the aerospace majors, I think it's in the third structures class when you get to this. And let's see, I think that's where they still do it. It's been a while since I looked at that, but some of you will see this later. But we don't cover it in this class in order to determine, is it going to do this? Or are we going to have local buckling? But I wanted to point that out just so you know why, if you bend something, it's still important to differentiate tension and compression, because somewhere later you might need that. Last thing I'll mention, because we're just about out of time, is you will see this formula in your textbook, I'm pretty sure. If not, I know a bunch of sources, you'll see this formula. Instead of sigma equals minus my over I, what you'll see is sigma max is equal to mc over I. Now, this is just disregarding positive or negative for tension or compression. It's just the largest magnitude of sigma, right? So we're not We're not doing any plus or minuses here. Where C here is the absolute value of Y max. Right? Because we talked about, if you look at this formula, your maximum stress is going to be where Y is the biggest, right? Y is the distance away from that axis. Well, that's going to occur at the top and the bottom surface. Now, if the cross-section is nice and symmetric, it would be the same distance to the top and the bottom. But that's not always true. Your beam is not always perfectly symmetric. Your centroid is not always right in the middle halfway. So it might be further to the top or the bottom. Whichever one's the furthest, that's what C is here in this formula. It's just the maximum distance from the neutral axis to the top or bottom surface. So whichever one of those is larger, that's what C is. You're just looking for the largest value you can put in there. And again, the moment, you're not going to put in plus or minus for the moment either. You're just going to put in what the magnitude of that moment is. No plus or minus is involved here. So if you are reading through the book, like hopefully you will, you see this formula, you understand the difference between these two formulas. And if the problem just simply asks you to find the maximum bending stress, this is what they're talking about. They just want to know what the maximum magnitude is. And if it asks you for the stress at some particular point on that cross-section, you would use this formula. If you want the maximum compressive stress or the maximum tensile stress, use this first formula. All right? Does everybody understand that? All right, so it's a good place. We got basically where we wanted to get these formulas derived so that Monday we're going to start applying this, and we're going to solve problems calculating normal stress using the formula that we developed today. So before I stop recording and wrap up in this session, any questions? All right, well then that's where we stop today. I'm going to stop recording as usual. If you got questions and want to hang around after, in a few minutes, I'll be able to answer any questions you have.